I would like to thank Professor Tien and his associates for all of their efforts putting on this wonderful meeting. Today, I'd like to talk about phonon-nuclear models and progress that we've made. The models are based on the phonon-nuclear interaction, which we derived previously from the Dirac model. So if we have a many particle Dirac model and we do a partial Foldy-Wolthusen rotation, we get terms that involve the center of mass momentum plus internal nuclear degrees of freedom, which is equivalent to having a phonon-nuclear interaction. Now, a headache is that the Dirac model is not covariant. So the question is whether the phonon-nuclear interaction derived from the Dirac model is good. To explore this, I put together a two-body model based on the Dirac model with a parabolic interaction between the two bodies and did some numerical calculations. One thing that I find is the energy momentum relation for the ground state is almost indistinguishable from that of a covariant system. So on this plot, there's a blue line and a red line. One is the calculation from the Dirac model. The other is the analytic covariant energy momentum relation that you would expect for a covariant system. The fact that the Dirac model is not covariant does show up in the relative energy shifts. In this case, this is the transition energy between the n equals 2 and the n equals 0, the lowest n equals 2 state and the ground state as a function of momentum. So this transition energy ought to be flat. It should be independent of how fast the body's moving. But since the Dirac model is not covariant, this varies. So the conclusion is that the Dirac model is reasonably good in that the energy momentum relation for the center of mass is excellent, and a minor shift in the relative state energies is why the Dirac equation is not used in the moving system. All papers in the literature in the rest frame. But the idea is that that gives us some encouragement that maybe it's good enough to do what's needed. As a check, we worked with the Bethe-Salpeter equation, which is covariant, and we considered a two-body version of it. We were able to use the partial Foldy-Wolthusen rotation, and what shows up is we get P dot P, we get terms that showed up in the transformation of the Dirac model, and we get a corrected or a modified interaction operator where the modification is very, very similar to what we get from the two-body Dirac model. So this gives us a confidence that the phonon-nuclear interaction derived from the Dirac model is actually okay. We've been working on models for excess heat for more than 3 decades at this point. So what I wanted to do is to summarize the basic idea. Because neutrons are uncorrelated or possibly anti-correlated with the excess heat, you can use that to place an upper bound on the energy that a helium-4 nucleus would have at birth. And the conclusion is that it would have to start out with less than 10 keV kinetic energy. If it had more than that, it would run into nearby deuterons and have knock-on deuteron-deuteron fusion reactions, which would make neutrons. We've been interested in coherent processes, which are linear in the matrix element, and they can be fast. The idea is that the gamma factor is about 10 to the minus 40th for molecular D2. And so the square of that would be 10 to the minus 80th. So this would show up for all incoherent reactions in the lowest order terms. And coherent processes, if they go linear in the matrix element, can be, will not have an extra 40 order of magnitude reduction at the outset. The scheme that we worked with, have been working with earlier this year, looks something like this. We do excitation transfer from the D2 helium-4 system to promote either a palladium nucleus to an excited state or an impurity nucleus to its excited state. Then excitation transfer with subdivision, basically this goes down and two other nuclei go up to roughly half the energy. There's a minor advantage if they're in the same state, but it's unlikely that we'll find a state exactly halfway down. Then another set of excitation transfers leading to 4 nuclei excited with roughly 6 MeV, 24 MeV divided by 4. And this down conversion continues until we have basically thousands of nuclei with relatively low excitation. And the idea is that this works best if reasonably stable states are found for this in all cases. And finally, for the last step is down conversion into vibrations. So at the end of the day, the D2 has been turned into helium-4. All the nuclei are returned to their ground state, and the vibrations have received the energy. So I've described previously many connections with experiment. If on the first step, if you had a 24 MeV excitation in palladium, you'd expect it if you weren't producing excess heat, so the population would leave, that if it decayed, it would produce roughly 20 MeV alphas. And here's some observation reported by Chambers of such emission. You'd also expect 14 MeV neutrons, which Vysotskii and Pambos have presented data for neutrons in that energy range. If there's 2 excited PDs with 12 MeV excitation, you get a variety of neutron energy emission, the highest of which is around 4.5 MeV, and then you get low energy neutrons below 2.5 MeV. This is some data from Takahashi, 1990. Anyway, there are other connections to be made. The overall process has to be coherent. So we've been working on matrix elements for the first step, matrix elements for phonon-nuclear transitions from ground state of nuclei. And we have models for the down conversion. Recently, a newer model for down conversion is being put together. But how do we assemble all of these pieces and parts? So if one thinks about it, since a lot of things happening, we have to calculate it as a single process. So perturbation theory would lead to an explosion of terms of this sort. So one approach would be to basically try to count them and evaluate, quantify them. Another approach was to use a matrix formulation. So I have a vector of interaction terms which connect the last step to things intermediate, and transpose vector for the first step from the initial state to everything intermediate. And then basically the possibility of having a big matrix inverse in the middle here to deal with everything that's happening in between the subdivision. This combined with some shortcuts, counting, combining terms together for down conversion, that kind of thing. It's quite possible that in the coming year, we can put all this together and get some reaction rates out of it. There's a level density issue. So in the case of D2 to helium-4 transition up at 24 MeV, we would expect there to be lots of levels. On the other hand, the levels aren't well known. In the density of states is well known, but detailed level structure is not known. On the other hand, in the NuDat2 database of Brookhaven National Lab, the nickel isotopes, the levels are known in the vicinity of the 5.5 MeV HD to helium-3 transition. So the question is, what does it look like? So here we've plotted the levels of the nickel, stable nickel isotopes, and here's the transition at 5.5 MeV. So there are clearly some states up here. Now the question is how close? So if we do a close-up of it, here's the HD to helium-3 transition energy. And nickel 62 has a state which is closest. It's on the order of 5 keV away. So that's a headache in the sense that we'd actually like levels that are much closer than 5 keV to the transition energy. So in principle, impurities, which have levels that are closer, would be useful. At some point, studies will have to be done to figure out which isotopes have levels that make a difference, but we haven't gotten there in the field yet. We'd like to have, in general, more nuclear levels such that the subdivision would be able to have an easier time matching energy. So impurities would be very helpful for that. For the low-lying metastable or long-lived states, would be helpful for down conversion. So here I've plotted all of the relevant excited states for stable, the stable nuclei, considering U-235 as being stable enough to post as well. We'd like to have transition stability lasting sort of between a millisecond and probably an hour. So this transition in scandium looks very interesting. Rhodium-103 probably is interesting in palladium experiments. I've always been a fan of this 201 mercury transition at 1.5 keV. So if nickel doesn't have isotope levels near 5.4, near the HD to helium-3 transition energy, the NuDat2 database has got excited state energy tabulations for many other isotopes. I mean, it's not complete because not all the states are known. But if we search through them, we get the following picture. The closest is that's known is a transition in tin-116, which is about 250 volts off. It's low. One thing that caught my attention when I did the study was cesium-137. This one's unstable, but all the rest of the transitions are in stable nuclei. This one caught my attention in part because of the Piantelli experiment. So in the Piantelli experiment, when I visited their lab, they showed me the 661 keV from transition showed up in their experiment at low levels. And turned on when excess heat turned on, which they showed me. And I have been thinking about that ever since. So the idea is if there's a close match between HD and helium-3 and this transition is cesium-137, then an excitation transfer would get you to an excited state of cesium-137. And the thought is that this state would decay faster by orders and orders of magnitude. So once you got here, it would go down. Now, a headache is that this is not on resonance. There's a 700 volt energy difference. So that is an issue. But the basic idea is that the normal decay is 30 years, but you have the possibility perhaps of speeding it up, basically by getting it more energy. So in the case, so Vysotskii and Kornilova worked with biological cultures and reported a 40 times increase in the decay of cesium-137. And if I were to think about that pictorially with the scheme, here's the cesium excited state position, And here's the HD position relative to helium-3. Now, if you exchange a few phonons, it doesn't go very far. You have 700 volts to make up, but a phonon's worth of energy isn't going to do it. On the other hand, in my models, if you're making excess heat, then associated with a phonon exchange, there can be exchange of a larger energy quantum. And under these conditions, you have the possibility of having resonant transitions, which has the possibility of giving you orders of magnitude increase in the decay rate. So I'm of the opinion that that this gamma is turning on because energy exchange is being allowed when excess heat is produced, allowing for this transition to occur with higher probability. What I'd like to do is make a new experiment, use cesium-137 basically as a marker for excess heat. So my initial thought is, suppose we start out with let's co-deposition, where we can make vacancies, which I think is where the excess heat's occurring. So let's co-deposition works with higher current density and lower concentration than PAN-VOS uses. And then dump some cesium chloride in the electrolyte. Now, the immediate headache that cesium doesn't co-deposit efficiently. On the other hand, we only need a small amount. We don't need like 50% or 20% of the deposited material to be radioactive cesium. But a few would allow us to do measurements to have the cesium where the excess heat's being produced. Now, if we're making vacancies, then perhaps that helps. Cesium's pretty big. So I've indicated in green here the cesium along lines of hydrogen or deuterium, where the vacancies are. So the idea is that we turn the thing on if we're making excess heat. Maybe the 661 kV turns on by orders of magnitude, which would be stunning to see, and we would learn a lot from this kind of experiment. The null reaction was the first excitation transfer process I looked at in connection with the cold fusion problem. So the idea is that a D2 goes to helium-4 here, and a helium-4 somewhere else goes and makes D2. My initial response was, well, this is cool because it's exactly in resonance. But at the time, I thought this is of academic interest only because how in the world are you going to see it? But now I'm beginning to understand that this is actually very, very interesting. And if you actually promote helium-4 to produce an excited state D2, or a D2 molecule, that when it gets created, the two deuterons are very close to one another. And as it turns out, they have a really tough time tunneling apart, which means they're not going to tunnel apart during the time of the experiment. So that is important in connection with excess heat, low-level nuclear emissions, and the Kasagi three-body experiment. So finally getting around to putting together a more modern version of the model for it. And if we start with, let's start several steps back and simplify and reduce, we get a problem that looks like this. So phonons, we've got the basically D2 and helium-4 system. These are nucleons and different nuclei here. And these terms are due to excitation transfer. Now, we can begin to get solutions to for this model. And we get a resonant tunneling effect. We get, I mean, I've been interested in resonant tunneling like forever. Xingjiang Li's been interested in it as well. And this model shows resonant tunneling. So we get the sort of the plus and the minus component states where the D2 state, the probability looks like this, and the compact state looks like this on a log ln kind of plot. So this is actually very localized at small relative separation on a nuclear scale. Now the issue is even though we get some in different states, the time scale needed, because they're nearly degenerate, the time scale needed to go between them is very long. So what this tells me is that if I've made D2 from helium-4, it's going to be a compact state, and it's not going to go through the Coulomb barrier. That immediately draws attention to the Kasagi three-body experiment, where he came in with 150 keV deuterons on a titanium deuteride and saw energetic alphas and energetic protons that appeared to be consistent with a three-body reaction, a deuteron hitting two deuterons close together. Now, if you've got this compact D2 state that's not tunneling, it could help solve the problem here, because 24 MeV state in a palladium excited state, you'd be hard pressed to imagine that that's going to hang around very long, although these states aren't well understood, so who knows. So if this first step were replaced by an HD promotion with a compact D2 state, this would basically solve some of the biggest problems in the model. This thing could then go down and give rise to excitation in palladium or other nuclei for the rest of the model. So this could be a modification, or is very likely to be a modification for the next iteration of the model. In connection with the alpha emission of chambers and the neutron emission for Vysotskii and Kornilova, we could include the compact D2 state as an intermediate state, which could transfer its excitation of palladium here. So the inclusion of this into the model throughout is straightforward. Matrix elements. To make these models work, we've got to calculate matrix element, and we've been working on these matrix elements. One advance is we've done a non-relativistic reduction in the case of one-pion exchange potential. We've also done the spin, isospin angular momentum reduction for the HD to helium-3 matrix element. And here's the radial matrix element that remains. As we can see, it's quite complicated. We've been working on nuclear models, putting together codes. Hopefully this summer, some of these codes will start to give us numbers. So we can use this to calculate phonon-nuclear matrix elements, as well as off-resonant energy shifts. So the idea is that if you have excitation transfer, you go through intermediate states that are off resonance. So these states are on resonance, this one's on resonance, this one's on resonance. So this energy line here is, if you're on there, you're on resonance. If you're away, then you're off of resonance. And the issue is that the nucleon-nucleon potential changes off of resonance. It gets stronger when you're low, it gets weaker when you're high. And this is a change in the binding energy of the deuteron when it's pushed off of resonance. So pictorially, for excitation transfer, the contribution from going one way and going the other way, they destructively interfere. So if these levels shift, if they shift differently on one side and the other, then you can break the destructive interference. That makes a huge difference for excitation transfer and also for up conversion, down conversion. So we've been working on models for down conversion, include this. For excitation transfer, we have models now. There's always ideas for new experiments. We've been doing excitation transfer experiments with cobalt and iron, and we've seen angular anisotropy. I've been trying to think about modeling this, and the very first thing that happened when I tried modeling it is I thought, wow, I'm having to average over all these very tiny pieces of the lattice. But if we had a single crystal and we had resonant excitation transfer, we would get a very well-defined beam out. Here's an example of calculation in 100 direction. It was about 10 times stronger than peaks 0.2 some radians off of resonance. Another experiment would be really interesting is to use our ion beam experiment and use uranium U-238. So the idea is that the decay of U-238 at 24 MeV excitation would involve a 27.6 MeV alpha, which would be exciting to see. So there are advantages, high density of states. Uranium probably has got helium in it. And Pam-Vosley reported some nice results from uranium. Here are some references. that are relevant to our work. And here's a picture of well, previous times. Thank you for your attention.